Section 6.3, proving quadrilaterals or parallelograms. In this section, we have 5 ways to prove a quadrilateral is a parallelogram. We're going to use a definition and properties from the previous section to do that. So these are going to sound very familiar. First, the definition. If I can prove both pairs of opposite sides of a quadrilateral are parallel, then that quadrilateral must be a parallelogram. In Theorem 5.6, if I can show that both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Theorem 6.6 says if both pairs of opposite angles are congruent, then the quadrilateral is a parallelogram. In Theorem 6.7, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Those 4 previous ways to prove a quadrilateral is a parallelogram. It should seem very similar to what we have done in the previous sections. There's only one new addition that's going to seem a little different, and that's in Theorem 6.8. Theorem 6.8 would be if one pair of sides is both congruent and parallel, then the quadrilateral is a parallelogram. On the previous slides, we know that this makes a parallelogram, opposite sides being parallel. That's the first slide that we looked at to prove a quadrilateral is a parallelogram. That's the first one. Number 2 would be is if I can prove opposite sides are congruent. The third one was if I can prove opposite angles are congruent. And on the previous slide, number 4, is if I can prove that the diagonals bisect each other. And all of these should seem very, very familiar from the previous definitions and properties. This one adds a little bit different look to it. And that is if I can prove one pair of sides is both congruent and parallel. If this occurs, then this is also a parallelogram. We need to keep these in mind when solving the problems in this section, and also when doing proofs of proving a quadrilateral is a parallelogram. In the next few slides, we want to use the diagrams and the information in them to determine if the quadrilaterals are parallelograms. And if the answer is yes, we want to state the reason why. Here's the first diagram. I have opposite sides being parallel. Therefore, this quadrilateral is a parallelogram by the definition of a parallelogram, both pair of opposite sides being parallel. In this diagram, again, the answer would be yes, but I think I could get 2 ways of doing this. One would be opposite angles being congruent. So both pair of opposite angles congruent. If I have both pair of opposite angles in a quadrilateral congruent, then it's parallelogram. I also believe I could state if 2 lines are perpendicular to the same line, then they must be parallel. And that occurs in both situations. So I could state that this is also the definition of a parallelogram, that both pair of opposite sides are parallel. In this diagram, I have one pair of sides that are parallel, and I have one pair of opposite sides that are congruent. Unfortunately, they're not the same side, because our theorem states that if one side is both congruent and parallel, then it's a quadrilateral. This is one pair of opposite sides congruent and the other pair of parallel. So the answer here is no. I either needed this segment to be congruent to that segment, then I would have the correct situation, or these 2 sides being parallel. In this diagram, I have one pair of opposite sides congruent and the information that the 2 angles are 138 degrees and 42 degrees. These 2 angles are cut by 2 lines and a transversal. Therefore, if I add these 2 together, I will get 138 plus 42, which is 180 degrees. And that is one of the converses of theorems we've had before, the converse of the same side interior angles, which would be if same side interior angles are supplementary, then the 2 lines cut by a transversal must be parallel. And that does give us one of the reasons to prove a quadrilateral is a parallelogram. One pair of opposite sides is both congruent and parallel. If one pair of opposite sides is both congruent and parallel, then it's a parallelogram. In this diagram, I'm given that both pair of diagonals bisect each other. This segment is congruent to this segment because it's 3 inches and 3 inches, and this segment is congruent to this segment because it's 5 inches and 5 inches. Therefore, this quadrilateral is a parallelogram because the diagonals bisect each other. And our theorem states if a quadrilateral has diagonals that bisect each other, then that quadrilateral is a parallelogram. In this diagram, I do have a quadrilateral. I have the diagonals, but only this diagonal is being bisected by the other one. I only have one pair of diagonals being bisected, and that does not qualify in our theorem, so the answer here is no. On this slide, they want us to find the values of x or y for which ABC must be a parallelogram. So we're given quadrilateral ABCD, and we need to have these values be congruent to make this a parallelogram. If these two values are congruent, these two angles are alternate interior angles. And if alternate interior angles are congruent, then these two lines cut by this transversal would be parallel. And that would make ABCD a parallelogram because if one pair of opposite sides is both congruent and parallel, then that quadrilateral is a parallelogram. So we need to make these two angles congruent. To do that, I just set these two expressions equal and solve for the value of x. 3x minus 8 equals x plus 20. I'm going to subtract x on both sides, get 2x. Add 8 to both sides, I get 28. Divide by 2, and my value for x is 14. I can substitute in to check that. 14 plus 20 is 34 degrees. And 14 times 3 is going to give me 42. 42 minus 8 is still 34 degrees. Now that these two angles are congruent, I know that the two lines cut by a transversal must be parallel. And that tells me that ABCD must be a parallelogram because if one pair of opposite sides is both congruent and parallel, then that quadrilateral must be a parallelogram. In this diagram, again, we want to find the values of x or y for which ABCD must be a parallelogram. Here we're given quadrilateral ABCD, and we want to assume that this is a parallelogram. Therefore, we need to find the value of y that makes these diagonals bisect. And I already have one pair of diagonals being bisected because they already have the tick marks in the diagram. Now I just have to set an equation with those expressions. 5y plus 7 equals 3y plus 21. I need to find the value of y that makes these two segments congruent, therefore they'll be bisected. I subtract 3y on both sides, that gives me 2y. Subtract 7, that gives me 14. Divide by 2, I get y equal to 7. I can check my solution. 5 times 7 is 35. 35 plus 7 is 42. 7 times 3 is 21. 21 and 21 is 42. Now I have a diagram, specifically a quadrilateral that has its diagonals being bisected. Therefore, ABCD is a parallelogram. On this slide, we want to prove that quadrilateral ABCD is a parallelogram. We're given angle BAC is congruent to angle DCA, and that angle B is congruent to angle D. Let's start with the first part. Angle BAC congruent to angle DCA. With that information, I know that these two angles are alternate interior angles. And if alternate interior angles are congruent, then the two lines cut by a transversal are parallel. Therefore, AB is parallel to DC. So I can state that on step 2. AB parallel to DC. And that is by the converse of the AIA theorem. If alternate interior angle is congruent, then the two lines cut by a transversal are parallel. The second part of the given is angle B is congruent to angle D. That does not give us both pair of opposite angles of the quadrilateral congruent. B and D are opposite angles, but these are not the entire angles of the quadrilateral, so I need more information. But I do recognize I have two triangles, and each of those triangles have two pair of angles congruent to them. Therefore, I can get these two triangles congruent. To do that, I just need to state AC is congruent to segment AC by the reflexive property. Now, having that information can get me my two triangles congruent. Therefore, I can state triangle BAC congruent to triangle DCA. And that is by the angle-side theorem. Once I have that, I can use corresponding parts of congruent triangles to get more information. Notice I already have one pair of opposite sides being parallel. I know a theorem that can help. If I can make these two segments congruent, which I can by CPCTC, so I'll state that, segment AB is congruent to segment CD by CPCTC, then I have that quadrilateral ABCD is a parallelogram. And that reasoning is by if one pair of opposite sides is both congruent and parallel, then the quad is a parallelogram. So that solves my proof. If one pair of opposite sides is both congruent and parallel, then my quadrilateral is a parallelogram. On this slide, I want to prove that angle A is congruent to angle F. I'm given ABCD is a parallelogram and FGCE is a parallelogram. In this diagram, I want to prove that angle A is congruent to angle F. I know that the large figure is a parallelogram. Therefore, I can state that angle A is congruent to angle C. So step 2, angle A is congruent to angle C. And that is because opposite angles in a parallelogram are congruent. I also know that this figure is a parallelogram. Therefore, I know angle F is congruent to angle C. I can put that on the same line. Because it's the same reasoning. Opposite angles in a parallelogram are congruent. Therefore, from that statement, I know that angle A and angle F are congruent to the same angle. Therefore, angle A is congruent to angle F. That is by substitution. And that is what I wanted to prove.